Hello everybody, and welcome to example 1 on page 39 of the workbook. And this is going to be our first example of actually calculating the exact value of a directional derivative. That's the theorem that we derived in a previous video. Well, actually we didn't derive it, we just wrote it down, but we're going to use it now. Okay, and this example involves the same temperature function that we used in the preliminary example, and actually essentially the same points P and Q. Q is a little bit different than the Q. I think I rounded off the first coordinate to 1.7, but you can think of this as being the same problem that we did in part B of the preliminary example where we found that approximation. Okay, so let's first draw a picture here. Okay, so we're trying to find the rate of change from P to Q. So I always like to draw the path just so that we can see it. So 1, 1, and 1.7 and 0.5. Okay, we're going from 1, 1 to 1.7.5, or actually we're moving in that direction. Okay, so there's the points P and Q. And I'm going to give that vector a name, just call it V. And let's take a look at what we need to do in order to find this derivative. The idea is we're going to use the formula up here that we just derived. Okay, so notice that we need two things to use that formula. We need the gradient, and we need a unit vector in the direction that we're moving. All right, let's start with the gradient. Okay, well, the gradient, we actually calculated already when we did the preliminary example. That just involved taking the derivatives of the with respect to x and y. Okay, I'm just going to write out that formula again. It kind of looks like this. Okay, and those two derivatives wound up being minus a half xi minus a half yj. Same formula for the gradient that we got in the preliminary example. Okay, and then just say a word to remind us of what we're trying to find. We're looking for the derivative of t at the point 1, 1 in the direction of v, that vector that we drew to the right. Okay, well again, we have the first piece that we need. Okay, to find a directional derivative, we have the gradient, but we still need a unit vector. Remember that caution. Okay, in order to use the formula that's above, we need a unit vector, and the vector that we have is not a unit vector. Okay, v, if you measure its length, it's not going to be 1. So we're going to use that process of scaling our vector so that it is a unit vector. That's going to be our next step here. So let's say it this way. We'll find a unit vector in the direction of this vector v. All right, and we can do that by just taking the vector v and dividing by its length. All right, so let's see. V is, okay, well, to get components for v, we can just subtract coordinates. So we're going from 1 to 1.7. That's going to be 0.7 in the I direction. And then going from 1 to 0.5, that's going backwards 0.5. Okay, so minus 0.5 in the j direction. So up there in the numerator is just the vector v, and then we're going to divide by its length to turn it into a unit vector. Okay, so over the square root of 0.7 squared plus negative 0.5 squared. Okay, and you can do the arithmetic there. Kind of divide those numbers, and what you're going to wind up with, just rounding off to 2 decimal places, is a unit vector that looks like 0.81i minus 0.58j. Okay, there's u. Okay, so now we have the two pieces that we need to find the derivative. We've got the gradient, and we've got a unit vector. Okay, and so we're going to use the formula from the top of the page to calculate this directional derivative. Okay, notation for that again is t sub u, derivative of t in the direction of u. Okay, and our formula tells us we just need to take the gradient at 1, 1 and dot it with that unit vector that we just found. Okay, so first, what happens if we take x equals 1 and y equals 1 and substitute into our gradient formula? Well, we're just going to get negative a half I minus a half j. Since x and y are both 1, we'll dot that with the unit vector from up here. Okay, and then take the dot product and see what we wind up with for an answer. And remember, a dot product is going to give us a scalar. We're just going to multiply corresponding components. Okay, and I'll leave it to you to just confirm my arithmetic here. That winds up being about minus 0.12. Okay, and what would the units on this answer be? Okay, well, this is a rate of change of temperature with respect to distance, so its units should be degrees Celsius per centimeter. Okay, and there is our directional derivative. That is how fast the temperature is changing as we move in the direction, as we move away from the 0.11 along this vector PQ.